Hi everyone, I am Shashank Dattathri, a former undergraduate student at the Indian Institute of Science and a current graduate student at Yale. In this video, I'll be talking about my work with Professor Prateek Sharma, which studies the cosmological evolution of baryonic gas and supermassive black holes in idealized isolated halos. The paper containing the full details of our setup and the results has been published in MNRAS. Broadly speaking, there are two classes of galaxy formation simulations. Full cosmological simulations examine the large-scale distribution and evolution of matter in the universe. On the other hand, idealized halo simulations are typically of smaller scales and higher resolution, and they are more phenomenological in nature. Our work is an effort to provide a middle ground between the two, which we term a semi-cosmological model. Using the Pluto hydrodynamic code, we carry out 2D simulations of gas in an idealized isolated halo, which is self-consistently evolving according to various cosmological prescriptions. Our setup is computationally inexpensive, which allows us to survey a large parameter space. Our simulations include the cosmological evolution of the dark matter halo, metallicity-dependent radiative cooling of the gas, evolution of the IgM and ICM metallicity, AGN jet feedback, and the growth of the central supermassive black hole. Star formation is not modeled in our simulations, but it can be implemented in the future. In order to study the evolution across time, we require an accurate model of the dark matter density beyond the virial radius of a halo. The NFW profile accurately models the density in the inner regions, but not the outer regions. Therefore, we use the profile given by Diemer and Kravtsov in their 2014 paper, which transitions from an NFW profile in the inner regions to a realistic outer profile, as shown in the figure. We use this dark matter density to construct the gravitational potential by numerically solving the Poisson equation. Over time, the gas cools and falls towards the center of the potential well. A fraction of this cold gas can make it all the way to the central supermassive black hole, which accretes onto its event horizon. This leads to the growth of the black hole, as well as feedback heating from AGN jets, which heat up the gas and eject it from the halo core. We can see that the physics at both the micro and macro scales together determine how the halo evolves. Several of these microscale physics cannot be resolved and therefore are modeled using separate prescriptions. Here we see how the core of the halo evolves during the simulation. The cold gas, represented in blue, falls towards the center, which can trigger the feedback, launching powerful jets into the ICM. This results in hot gas being ejected from the core in the form of bubbles and cavities, which is shown in yellow. Over time, the hot gas rises buoyantly and mixes with the surrounding medium. In the absence of continued feedback, the gas starts to cool and flow inwards again, and thus a self-regulating cycle of cooling and heating is formed. We can see that the heating portion of the cycle is characterized by a high accretion rate onto the black hole, a high value of T cooled by TFF, large jet power, and lower mass of cold gas, and vice versa for the cooling portion of the cycle. The black hole initially grows exponentially with time, corresponding to the quasar phase, but then slows down at later times, which is the self-regulating radio phase of evolution. Finally, we analyze how the evolution of the gas and the growth of black holes are correlated with each other. Our results show that the values of halo mass, black hole mass, and cold gas inflow rate lie on a fundamental plane. This suggests that their evolutions are strongly linked. Our simulations show that on average, more massive black holes are found in more massive halos, as well as quiescent galaxies compared to actively star-forming galaxies. And this is in line with several observational results. Our idealized setup captures several important physical processes governing the evolution of halos. However, more work is certainly required to study the full interplay between the small-scale and large-scale physics, and to resolve the interstellar medium of the central galaxy. In addition, since our simulations are in 2D, they cannot capture some of the important phenomena that only occur in 3D. A link to the article is provided below in the description, and feel free to contact me for any questions or discussions. Thanks for watching. Please subscribe to the channel for more about astrophysical simulations.